If you buy like a $10 phone charger online, moving it the last 5 miles to your house often costs the company more than shipping it 5,000 miles across the ocean.
Oh, absolutely. It's wild.
Right. That massive discrepancy is just the brutal reality of logistics network design. You click buy, you track that little delivery truck icon on your phone, and you expect absolute precision.
Yeah, and you want it by tomorrow.
Exactly. But behind the scenes, getting that box to your doorstep without bankrupting the company, I mean, it's this high-stakes, multi-million-dollar puzzle.
You really do live or die by the network you build. I mean, these are massive capital investments. Sometimes they take years to execute.
For sure.
Finding the absolute perfect place to, pour concrete for a distribution center, or mathematically modeling how to route global shipments to hit a specific delivery window.
Oh.
Getting that right provides the ultimate strategic advantage.
It's like an invisible moat around your business.
Exactly. One that competitors simply cannot cross.
Which is exactly what we are getting into today. So welcome to the deep dive. Our mission today is unpacking Module 9, Section C of the APCS CLTD learning system.
A really fascinating section.
It really is. We are going to explore the formal process of network design, looking at how organizations evaluate that delicate balance between transportation and facilities.
And the mathematical models they use to stick a pin on a map.
Yes, and how they actually prove their designs will survive contact with the real world.
Because the overarching goal is incredibly complex.
Hmm.
You're attempting to find the optimum mix of inventory, warehousing, and transportation costs.
Right. You can't just maximize one and ignore the others.
No, not at all. You have to deliver the necessary service levels at a price your customers are actually willing to pay, all while engineering enough margin to, generate a profit.
Okay, let's unpack this. Before we even talk about finding the perfect plot of land, we need to understand the catalyst. Because pouring concrete is expensive. Breaking leases is expensive. Why would an organization willingly blow up a multi-million-dollar network? Like, what actually triggers this kind of massive redesign?
Well, the sources outline a few critical drivers for change, and it really starts with the relentless pressure of rising customer expectations.
Which never stop going up.
Exactly. Consumer behavior evolves so rapidly. If a competitor suddenly normalizes next-day delivery, and your legacy network was meticulously designed over 10 years for a 3-day turnaround,
You're in trouble.
your entire infrastructure is suddenly a massive liability. You are effectively obsolete overnight.
The bar just keeps getting raised. You have to re-engineer the machine just to keep up.
Yeah. Another massive driver is mergers and acquisitions.
Oh, that makes sense.
Right. When two enterprise-level companies merge, they're instantly saddled with a Frankenstein logistics network.
Just two completely separate supply chains mashed together.
Overlaid right on top of each other. And if they don't redesign it, they are bleeding cash by operating redundant facilities.
Like paying for two massive distribution centers in the exact same industrial park.
Exactly, when they only have the demand to justify one. To capture the economies of scale that justified the merger to the board in the first place, they have to consolidate.
That makes perfect sense. I mean, you buy a rival, you don't keep their redundant overhead. But what about internal changes, like fundamentally shifting what you are actually selling?
Oh, that's a big one too. Introducing entirely new product families often requires specialized capabilities that your current network just cannot handle.
Like what? Give me an example.
So if a traditional consumer goods company acquires a pharmaceutical brand, or, they start selling perishable food.
Oh, right. You can't put that in a normal truck.
Exactly. You can't just toss those items on your existing dry van trailers. You have to design a cold chain.
A cold chain, right.
Yeah, a highly monitored, temperature-controlled supply chain with entirely different carrier contracts, specialized warehouse insulation.
And strict regulatory compliance, I imagine.
Oh, incredibly strict. Add in geopolitical shifts in global trade, fluctuating commodity prices, or nearshoring trends, and successful organizations are forced to constantly reassess.
The sources basically say if a network hasn't been evaluated in 5 to 7 years, the math almost guarantees it is inefficient, right?
100%.
But realizing your legacy network is obsolete is one thing. You can't just, pause global operations to fix it.
No, you definitely cannot.
We are talking about keeping the revenue flowing while tearing up the floorboards. How do you redesign the plan while you're flying it?
It's tough. The texts detail a rigorous 4-step formal process for supply chain transformation to mitigate that exact chaos.
Okay, let's walk through those steps.
Step 1 is creating the rationale and urgency. which basically translates directly to securing executive buy-in.
Because it's going to mess with everyone's workflow.
Right. A project of this scale will disrupt every single department: sales, finance, IT operations. Without air cover from the absolute top of the organization, department-level resistance will kill the project before it even starts.
So you need the CEO telling everyone, hey, this is happening, deal with it.
Pretty much, yeah. Step 2 is preparation. You form a dedicated project team, clearly define the scope, and execute an exhaustive as-is audit of the current network.
So mapping out what you actually have today.
Comprehensively. You're quantifying inventory days of supply, mapping every single transportation link, documenting carrier performance, all before you even sketch the to-be state.
You know, that as-is audit makes me think about a major home renovation.
Oh, how so?
Well, you can't just walk into a house with a sledgehammer and start tearing down walls to open up the kitchen.
Right.
You have to pull the blueprints, you have to map out the existing plumbing, you need to find the load-bearing walls, you have to trace the electrical runs.
That is a perfect analogy.
Because closing down a major distribution center is basically like knocking down a load-bearing wall. If you don't know exactly what inventory flows through it, the roof caves in on your entire operation.
Exactly. And once you know where the pipes are, step 3 is execution.
Right.
But this is where you carefully decompose the value streams and run pilot projects.
So you don't just flip a switch and turn the new network on globally?
Oh, absolutely not. That would be a disaster. You use a portfolio manager to sequence the rollout. They might launch the new design in a single low-risk geographic region first, proving the concept and working out the bugs.
Just to ensure the rest of the company continues operating smoothly.
Right. And finally, step 4 is the review phase, where you sustain the improvements, measure against your initial baselines, and establish a culture of continuous planning.
I imagine the people doing this aren't just moving straight down a checklist, right? Like checking off step 1, then step 2, and never looking back.
No, not at all. The sources heavily emphasize that this 4-step process is intensely iterative. As you move into the preparation phase and begin crunching the data on facility costs, you will likely discover that your initial assumptions from step 1 were completely wrong.
Oh, wow. So you just have to start over.
Sort of. The math might show that servicing a new market is unprofitable under your proposed design. That forces the team to loop back, completely refine their initial objectives, adjust the scope, and run the numbers again.
So it's this constant loop of testing feasibility and pivoting based on the data.
Exactly.
Well, let's get into the math that forces those iterative loops. This brings us to what seems like the most brutal reality of logistics, the inherent, unavoidable conflict between transportation costs and warehouse costs.
It really is the absolute core tension of network design. You are managing a seesaw of trade-offs.
Right.
On one side, you have the immense fixed costs of opening facilities and the working capital tied up in holding inventory. And on the other side, you have the variable costs of moving that inventory across the map.
And the sources highlight this perfectly with the total cost analysis curve.
Yes, Exhibit 931.
Right. Let's say a company decides they want to add more distribution centers to their network. The moment you add a new facility, your local delivery costs drop dramatically.
Because you are physically placing the product closer to the end customer.
Exactly. So that final mile of delivery becomes incredibly short and inexpensive. But the trade-off is severe. Your primary transportation costs, meaning the inbound freight moving goods from your manufacturing plants to all those newly scattered facilities, shoot up.
They absolutely skyrocket.
And obviously your fixed facility costs increase too because you are paying rent, utilities, and management salaries on multiple buildings.
So there is a mathematical sweet spot you're trying to calculate. When you transition from operating a single centralized distribution center to operating perhaps 3 or 4 regional centers, your total aggregated costs usually drop.
Because the massive savings you achieve on that final mile local delivery outpace the new building costs.
Exactly. But if you keep sliding down that scale, expanding to 6, 8, 10 facilities, that total cost curve spikes aggressively back up.
Okay, I have to push back here because logic kind of suggests otherwise.
All right, let's hear it.
If adding a warehouse gets the product to the customer faster, and we know it slashes those local delivery costs, why not push it to the extreme?
What do you mean?
Why not place a highly automated mini warehouse in every single major city? You would guarantee same-day delivery for everyone and make local shipping practically free.
I mean, in theory, sure. But the compounding penalty of inbound freight and inventory carrying costs would completely obliterate your profit margin.
Really? Just from the inbound freight?
Think about the inbound transportation dynamics. If you operate 5 massive regional hubs, your factories are sending product in full truckloads.
Right, TL shipments.
You maximize the cube of the trailer, which gives you the lowest possible cost per unit for transportation. But if you shatter that volume across 50 mini warehouses, you no longer have the demand to fill entire trailers for every location.
Oh, I see. You are forced to utilize LTL freight, less than truckload.
Exactly. You are shipping pallets instead of full trailers. And the cost per unit skyrockets. You are trading pennies in local delivery savings for dollars in inbound freight penalties.
Wow, okay. That makes sense.
But the real margin killer is the inventory itself. The texts detail a mathematical principle known as the square root rule.
Right, the square root rule.
It basically estimates the exact penalty your safety stock takes when you expand your network nodes.
Okay, let's slow down and run the actual numbers on this to make the pain real for you listening.
Good idea. So the formula calculates the square root of your proposed future number of facilities divided by your existing number of facilities and multiplies that by your current aggregate safety stock.
Okay, let's use an example. Let's say you currently operate a highly efficient network of 3 facilities.
Right.
And you want to add just one more to capture a new market, taking you to 4.
So you divide 4 by 3, getting roughly 1.33.
And the square root of 1.33 is roughly 1.15.
Exactly. Meaning, just by adding one single building to the map, your baseline safety stock across the entire global network has to increase by 15%.
Just to maintain the exact same statistical level of reliability against stockouts that you had yesterday.
Precisely.
A 15% increase in safety stock is not just a line item on a spreadsheet. We are talking about tying up millions of dollars of working capital in extra inventory.
Huge amounts of capital.
You have to lease the physical rack space to store it, pay insurance on it, and absorb them. So the sheer volume of redundant inventory required to feed that ultra-decentralized network would bankrupt most companies.
Without a doubt.
So, okay, assuming a company runs that rigorous total cost analysis, factors in the square root rule, and finds their mathematical sweet spot, let's say the data proves they need exactly 4 regional hubs to balance out all these costs and maximize margin.
Okay, 4 hubs.
The next logical hurdle is geography. We have 4 abstract pins, but how do we determine their physical coordinates?
This is where the team transitions from cost theory into advanced computer modeling. The APCS texts detail a hierarchy of approaches used to evaluate the map, and the baseline approach utilizes heuristics.
Which is essentially a trial and error rule of thumb methodology, right?
Basically, yeah. It trades absolute mathematical perfection for speed and computational ease.
Okay.
You leverage industry experience and established rules to filter a massive, unwieldy data set down to a handful of viable options.
And the sources detail a very specific heuristic called the center of gravity method. Let's walk through how that actually works in practice.
Sure. Imagine laying a massive XY coordinate grid over a map of your entire service area. You plot the location of every single customer or retail store on that grid.
Okay, like a giant math graph.
Right. The center of gravity method calculates a central coordinate, but it heavily weights that central point based on shipping volume.
So, if I have a massive manufacturing client in Chicago buying 10,000 tons of steel a month, and a small client in Peoria buying, say, 100 tons, the physical center of the map is halfway between them.
Right.
But the center of gravity formula forcefully pulls the coordinate toward Chicago because the transportation penalty for moving that heavy volume is so high.
Exactly. It gravitates toward the weight and volume, giving your real estate team a highly targeted search radius for a single facility.
Here's where it gets really interesting to me. The analogy I like to use is that heuristics is kind of like using a magnetic compass.
Oh, I like that.
It tells you generally to head north. It gets you into the right neighborhood quickly without overthinking it. But the next method, the texts discuss optimization, that is like a high-tech GPS system analyzing real-time variables.
That's a great way to look at it. Optimization utilizes highly complex mathematical models, primarily advanced linear programming.
No rules of thumb here.
None. It doesn't guess. It mathematically calculates the absolute ideal maximum or minimum value while actively balancing multiple conflicting constraints.
Conflicting constraints basically being the reality of business. Like, you want maximum operational efficiency, but you also demand maximum agility and responsiveness.
And you simply cannot have 100% of both simultaneously.
Never.
So the optimization software evaluates an overwhelming number of variables, fluctuating labor rates, localized taxes, variable transportation tariffs across different modes, strict service level agreement.
Just a massive amount of data.
It runs millions of iterative combinations in multidimensional space to output a network design that theoretically maximizes absolute profit, rather than just minimizing operational costs.
Which brings up the classic garbage in, garbage out problem. I mean, the model's perfection is entirely dependent on the data you feed it.
This raises a really important question about the hidden danger of optimization software, which is bad baseline assumptions.
Right.
If the project team feeds the model an assumption that calculates the transportation distance between a proposed warehouse and a major market as the crow flies.
Like a straight, unimpeded line on a map.
Right. The model will output a mathematically flawless answer based on that straight line.
But trucks don't fly.
Exactly.
They're bound by the physics of road networks. They have to detour around mountain ranges, they get bottlenecked at toll bridges, they face severe weight restrictions on local roads, and they sit in predictable rush hour traffic.
And if you fail to utilize actual granular road network and traffic data, your million-dollar software suite will confidently hand you a perfectly optimized set of coordinates that places your new distribution center at the bottom of a lake.
Or on the wrong side of an impassable mountain pass.
Right, which is why the models have to be validated. And that leads directly into the third approach, which is simulation.
Okay, simulation.
Simulation steps away from finding the single optimum answer. Instead, it leverages software to construct a digital twin of your proposed supply chain.
So you recreate the entire network in a virtual environment.
Complete with all its rules and constraints, specifically so you can introduce chaos.
Ah, I love this. You get to see exactly how the network shatters before you spend a dime pouring real concrete.
You run intense what-if scenarios. What happens to our service levels if global fuel prices spike by 40% overnight?
Or what happens to our safety stock if a major hurricane completely takes our East Coast hub offline for 2 weeks?
How does the network reroute? Simulation allows you to stress test the behavior of the system under extreme conditions and alternative operating policies.
So our optimization model, stress-tested by our simulation software, has finally spit out the mathematically perfect coordinates for our 4 new facilities.
All right, we've got our spots.
The software says, we are good to go. Can we finally start digging?
Well, the mathematical coordinates only get you into the neighborhood. Now the team has to evaluate the ground reality.
There's always a catch.
You have to analyze the physical dirt, the local political climate, and the financial spreadsheets to validate if this theoretical design can actually operate.
The sources refer to these as site-specific factors. It goes way beyond just being in the right zip code.
Way beyond.
You have to aggressively evaluate municipal zoning laws. Will the local government even permit a massive 1 million square foot industrial facility on that specific plot?
And you have to conduct geological surveys. A modern distribution center utilizes massive concrete slabs designed to support heavy automated storage and retrieval systems.
So the dirt literally matters.
Can the local soil topography actually bear the compressive weight of thousands of tons of steel racking and constantly moving robotics without settling and jamming the machinery?
Okay, let me ask a blunt question.
Go for it.
If I am a massive online retailer and my only goal is to stack millions of pallets of inventory as cheaply as possible, why not just buy the cheapest possible farmland 50 miles outside of town?
I mean, people try that.
Right. Why do things like local municipal noise ordinances matter if I own the land free and clear?
Because infrastructure failures and local regulations are absolute disqualifiers, regardless of the real estate price.
Oh, I see.
If you buy cheap land on an unreliable power grid that suffers from frequent brownouts, your automated sorting machines reset constantly. Your entire operation grinds to a halt.
So cheap land becomes very expensive.
Exactly. And if that cheap municipality enforces strict noise ordinances that prohibit commercial truck traffic between 10 p.m. and 6 a.m., your meticulously planned outbound order cycles are destroyed.
Wow. Yeah.
That cheap warehouse instantly becomes a crippling bottleneck that delays every single customer delivery by 12 hours.
The operational friction basically makes that cheap land incredibly expensive over a 5-year horizon. And we also have to consider clustering, right?
Oh, proximity is vital. You aren't just looking at the distance to your end customer.
Right.
If you are a high-tech manufacturer, there is a distinct reason you might accept the astronomical real estate costs of locating in Silicon Valley. You require immediate physical proximity to a highly specialized ecosystem of component suppliers and engineering talent.
The same logic applies to automotive manufacturing clusters in Germany or Mexico.
Exactly.
So the sites are selected, the dirt is turned, the buildings are up, and the trucks are finally rolling.
The dream is realized.
But how does the executive team know if this multi-year nightmare actually worked?
Well, validation is entirely dependent on establishing smart goals before the project even begins.
Specific, measurable, attainable, relevant, and time-bound objectives.
Exactly. Once operational, you validate through aggressive benchmarking.
So we are measuring ourselves against the industry heavyweights.
You compare your internal metrics against world-class competitors. The sources emphasize utilizing frameworks like ScoreDS.
Which gives everyone a universal language for performance.
Right. It provides a standardized dictionary of metrics. If you want to benchmark your order fulfillment cycle time, you have to know that your competitor is calculating that exact metric using the identical start and stop triggers.
Otherwise, you're just making it up.
Without a standardized framework like ScoreDS, you are comparing apples to oranges, and the benchmark is totally useless. And finally, the ultimate validation is a strict financial performance evaluation.
The hurdle rate.
Yes, the project team must definitively prove that the actual operational cost savings and new revenue generated by the redesigned network exceed the cost of the capital borrowed to build it.
So if your investors demand a specific return on capital and this new network fails to clear that financial hurdle rate,
the project is categorized as a failure, regardless of how efficient the delivery trucks look.
brutal. So what does this all mean for you listening? The next time you hit buy on your phone for a $10 item, pause and think about the sheer magnitude of what you just triggered.
It's massive.
Think about the carefully optimized network of cost trade-offs, the millions of dollars in square root safety stock formulas, the digital twin stress tests, and the local zoning battles that all had to be perfectly aligned years in advance just so that single box could arrive on your porch exactly when promised.
It is an absolutely stunning achievement of human coordination and mathematical modeling.
It really is.
The scale is remarkable. But if we pull back and connect this to the bigger strategic picture, the source material leaves us with one final, deeply provocative consideration.
Oh, what's that?
We spend all this time and capital optimizing networks and stripping out costs to maximize efficiency. But what happens when a network gets too lean?
You cut so close to the bone that you hit an artery?
Exactly. A perfectly optimized, ultra-lean supply chain is incredibly profitable on a spreadsheet. And in a perfect world, it is highly efficient. But mathematically, it is incredibly brittle.
Brittle. How so?
If you optimize down to a single global supplier for a critical microchip and route everything through one perfectly placed distribution center, you have engineered all the redundancy out of the system. If one single node fails due to a geopolitical conflict, a natural disaster, or a localized labor strike, the entire global system shatters.
Because there is zero shock absorption built into the design.
Precisely. Conversely, a slightly more complex network, one with redundant regional suppliers and slightly more buffer inventory than the optimization software says is strictly necessary, is much harder to manage and more expensive to operate.
Put it safer.
It is infinitely more resilient. The operational risk is spread out. So the next time you look at a highly efficient, ultra-lean corporate supply chain, ask yourself, is it truly optimized for the real world, or is it just waiting for a single excuse to break?